Swayam Prabha. Digital India. Educated India.
So, we discussed power swings in the last lecture. We had stopped here where we drew the power swing on the Rx plane and looked and saw what the relay would see on the Rx plane. So, this is what the impedance seen by the relay is. So, we also showed that these two angles, because of the side angle side, are equal, the alpha by 2 and alpha by 2. But if you see what the alpha by 2 is, this side is zt by 2 as we discussed. This side is zt by 2 cot of delta by 2. So, what we have here is tan of alpha by 2 is equal to zt by 2 divided by zt by 2 cot of delta by 2, which implies that tan alpha by 2 is equal to tan of delta by 2, which in turn implies that alpha is equal to delta. So, what you have here is these two angles are delta by 2 and delta by 2. If you remember, the angle between ES and ER is delta, because ES was ES angle delta and ER was ER angle 0. So, what this impedance locus now subtends the angle at the two extremes of ZS and ZR is the angle of separation between ES and ER, which is nothing but delta. Okay. So, when the delta changes due to the swing, as we saw in the equal area criterion discussion, when that changes, this delta also changes. Okay. So, this is because it is the same delta in any case. So, what happens is when delta, when the swing takes place on the Rx plane, it actually appears like this. Okay, this is your ZS, this is Z line, and this is ZR. Okay, of course the angle is closer to 90 than what I have drawn here, but for the sake of illustration, this would do. This is ZR, and the portion between ZS and ZR is ZL. Okay, and this is the angle that is subtended. It seems a bit closer, but in actual practice it will be a bit far, because this delta is very small. Okay. So, this is the apparent impedance as seen by the relay. The relay is sitting here at this, if you remember, it is sitting at the origin. Okay. So, now when delta changes due to the swing, what is happening is this, we have drawn this, we have made certain assumptions like ES equal to ER and all that, due to which this you get this, and this is ZT by 2 here and ZT by 2. Okay. So, now this delta will move along this trajectory here. Okay. When there is a swing, it will move, it will change from whatever delta there was and start increasing. If you remember the equal area criterion, the swing curve that we drew, for a line, this is the, okay, and this was the initial operating point delta naught or whatever that is. This is that delta here, delta or delta naught, not to confuse, to maintain a common terminology. If this is delta naught, then this will also be delta naught, and then delta goes on increasing. What it means is that since this delta was small earlier and now it has increased, it is moving in this direction. If the swing is stable, after some time delta will start reducing again. Okay, it will come to this direction here. It goes up to some delta max here, delta max, and then it will start retracing its path backward. So, it will come up to some delta max here and then start going back, and this oscillation will continue till after the fault is cleared, it settles back at delta naught. So, the thing of interest for us here is that what does the relay see? Now, if you plot the relay characteristics here, say this is zone 1. These are we are typically again looking at more relays. Sorry, this is a bit out of scale, so I will draw it again. About say 80% of the line or so. Say here, this is the line that we said. So, till here will be the zone 1. So, something like this will be zone 1 circle. Then you have the zone 2. It need not necessarily be within ZR, but let us assume that in this case, okay, and this is zone 3. Now, as long as this swing trajectory of delta stays outside of this zone 3, this is Z1, Z2 and Z3, there is no issue at all. Once it enters here, say your delta max is very large, okay, very large, say your delta max is somewhere here, not beyond this point, because once it goes beyond here, then you do not have the, you will not get any decelerating area equal to accelerating area and delta max, say delta max dash. So, say delta max dash is a little exaggerated, but say it is here. Okay. Now, if it comes into zone 3 and stays inside of zone 3 for a long enough time, then the relay does not know that it is a swing. Okay. Not yet, we will see what can be done about that a bit later, but the relay does not know it is a swing, it just sees an impedance which is inside its zone of operation, and if it stays long enough, usually if it is a stable swing it will move away, but if it stays inside for long enough, then the relay will issue a trip command. So, this is what happens is tripping on power swing. Okay, this is one of the issues that affect distance relays. Some other issues we saw last time like load encroachment, but this is one of the major issues with distance relays. Now, what happens if the swing goes beyond this point and then continues? If we saw that here the this is PM, so PM minus P is again positive, so that the acceleration will continue, and then if once it reaches this point, this is 180 degrees. Okay. So, now at 180 degrees what happens if this delta here is 180 degrees, means the locus is on the line itself. Okay. Delta equal to 180, the locus is on the line itself, and this point is known as the electrical center. Why it is known so, we will just see in very shortly. So, this is known as the electrical center, and what happens at electrical center is, because the locus lies on the line, the relay sees it as a 3-phase short circuit. And will issue an immediate trip command. Okay. So, for the relay it is impossible now to distinguish whether it is a fault or a swing, and it will issue an immediate trip command. So, why is it known as the electrical center? We will see that first, and then we will look at other issues of how to block the power swings, is it necessary to block the power swings, etc., etc. Okay. So, just for the sake of discussion now, assume that this was our this is our Zs plus Zl plus Zr, that is total Zt, that Z total. This is the sending end voltage, and let us take this as a reference here. So, it is fixed at some angle here. For the sake of this argument, let us assume that it is angle 0. The earlier argument was of delta, and then we have an ER here, okay, and this is initially at some angle delta. Now, as delta increases because of the power swing, this starts increasing, okay, and once it reaches 180 degrees, it will be here, okay, and if you join these two, you will see that now with some using some geometry here, you can see that the magnitude of, we have assumed that Es equal that that assumption still holds, and this side is equal, this angle is equal, this angle is 90 degrees, it is equal, and this angle is also equal. Okay. So, you have angle side angle, and the triangles are similar. So, this side is also equal to this side, and because of this equality, each will be equal to Zt by 2. So, this is the electrical center. Okay. And because it lies virtually at the center, it is known as the electrical center. One thing you will notice is that when the electrical center is formed, okay, the machines are out of step with each other, because they are 180 degrees apart, they can no longer operate synchronously, and we have to do something, we will have to separate the two. Synchronous machines, or if they are two groups of machines, we will have to separate the two, because synchronous operation is no longer possible. There will be a large voltage, large variation in voltages and currents, and that would lead to equipment damage. Now, we will have a look at the slides, because the commentary on this is a bit clear here. We will come back to electrical center very shortly. So, just some aspects of the plotting of the swing on the relay Rx plane. Some of the points are mentioned here, that this is exactly what we discussed, that when the angle subtended between by the locus on S and R and the endpoints is angle delta. When this angle becomes equal to 180 degrees, this is known as the electrical center, and it intersects the line impedance. Now, this as we just discussed is an indication of system instability. Okay. You can see here what we just saw on the drawings. Okay. Now, one aspect of the power swing is that you will not have all the assumptions hold. You know, we have assumed that Es equal to Er, the impedance angles of Zs, Zr and all that are equal, and the line are equal. Here, if what happens if Es and Er, the magnitudes are not the same. Okay. If they are the same, Es, the magnitude of Es equal to Er, you get this straight line here. More likely that if Es is not equal to Er, then it will be in the form of these curves. If Es is less than Er, I am talking of the magnitudes, not the not in terms of the angles of the two, but just if the magnitude of Es is less than Er, then you get this swing, the lower green curve that is shown here. If the magnitude of Es is greater than that of Er, then you get the upper curve. Okay. So, more likely in a system ES and ER magnitudes may not be equal. So, you will see one of the two curves, not the straight line as we have shown. Okay. It can be this can be shown analytically. We are earlier in the proof we had assumed that k is equal to 1. Okay. So, this is the electrical center that has been formed. We just saw in the notes, and this actually will lead to the tripping of the distance. Now, there are some aspects of the electrical center that we will discuss. One is that it is not some electrical center is not some permanent locus that is present. Okay. Because it is a swing and because the delta is continuously changing, the electrical center itself is not stationary. So, the electrical center is not stationary. Is not stationary. Okay. It will appear, and if the no relays trip, and somehow if you are able to hold the generators, this will never happen, but assume for a minute that no action is taken and this swing continues, then it can reappear. Okay. After these swing frequencies, after one period of the swing frequency. Okay. So, the first aspect is it is not stationary. The second is of course that it need not appear on the transmission line or at the center of the transmission line. Okay. So, if you remember our discussion, this is say ZS, then this is ZL, and this is ZR. Okay. So, if ZS is equal to ZR and all the other conditions, then it will lie exactly at the center. But suppose if ZS is very large, you have a very small synchronous machine, or the network behind is very weak, then ZS is very large. So, if ZS is very large, say for example, say ZS is this and ZL is very short transmission line, then it is possible that the electrical center could lie somewhere here on the machine or on some other transmission line behind the line that we are, or behind the relays that we are interested in. Then you would need a relay which is looking backward, and then which could sense the swing. So, this condition can happen when ZS is very large when compared to ZL. So, what this point implies is that it need not necessarily lie, the electrical center, I am abbreviating it to EC, need not lie on a transmission line. It could lie on a generator, or say a generator and a transformer together. It could lie on the transformer also. Okay. So, one more aspect is electrical center is not unique. Here it seems that there is only one electrical center, but a very simple example can be given. Say you have a generator connected, this could be the internal impedance or maybe the transformer impedance, and then you have say 3 lines. Okay, we have 3. I have shown the line as impedances, but just for the sake of convenience, there could be you could represent it as an RXB line also. So, this is ZS, this is ZL, these are the two sources ES and ER. Okay. And if the electrical center were to occur, then it could assume that they are is occurring on the transmission line only, and this could be the electrical center. So, you have got 3 electrical centers. If there was only one line, then you would have only one electrical center, but now you have got 3 electrical centers. So, you can have more than one. Okay. Also, you could have more than one if there are multiple modes of separation. Okay. So, you can have multiple ECs or multiple electrical centers. I am just abbreviating the same. In one case, if you have parallel lines or parallel paths this could be a transmission line where there is one transmission line and from one node to another, and from multiple nodes also it could come. So, parallel lines or parallel paths, and then multiple modes of separation. Okay. So, now having discussed this, what happens to the relay, that also we saw that it could come into the relay characteristics. And okay. So, now if it enters zone 3, if what will be the condition of the locus entering zone 3? If delta max is less than delta of zone 3, this is the delta zone 3, the angle that the locus subtends to the two ends of the line, okay, the impedance locus. So, if that this is delta Z3, if delta max is less than delta Z3, you do not have to worry. Okay, that means it is outside, it is somewhere far off from the relay characteristics, and it will not affect the relay operation. Okay. If on the other hand, if the delta max is between delta Z3 and delta Z2, what are delta Z2? It is the angle subtended by the zone 2 character at the point where the zone 2 characteristic intersects the locus, and delta Z1 similarly for zone 1. So, if delta Z3 is if the delta max is less than delta Z3, then you do not have to worry. If it is between delta Z3 and delta Z2, then the swing will enter zone 3. If it is between delta Z1 and delta Z2, then it has entered both zone 2 and zone 3. And if it is greater than delta Z1, then of course it has entered zone 2, zone 3 first, zone 2 and then zone 1. And here there is no wait time. If you remember, delta zone 3 and zone 2 have some coordination time intervals. Zone 2 will definitely have more than 300 milliseconds or so, 250 to 300 milliseconds, and zone 3 will definitely be more than 500 milliseconds. So, there is enough time. If it is a stable swing, the delta max will start reducing and then it will go back and the relay will not trip. But if it enters zone 1, then the relay will issue an immediate trip command. Okay. Now, what happens when this phenomenon of the encroachment of the relay characteristic by the swing characteristic takes place? Okay. So, what could happen is the relay will issue a trip command, and the breakers at the two ends of the line will open. Now, one might say that if it has entered zone 1 and the relay has issued a trip command, then it is I mean, anyway the stable system operation was not possible. So, if the islanding has occurred or the separation has occurred, it may be a good thing. That is not necessarily the case, and mostly it will never be the case, because I will just explain it with an example. Say you have a system like this. Okay. You have two generators and 3 buses in okay, and say the loads are, we will write it in terms of per unit, and this is the generation here is 0.33 per unit, and the load and the generation here is 0.66 per unit. Okay. The load here is 0.33 per unit, each has 0.33 per unit. So, roughly 1 pu, not exactly, but say 1 pu load and 1 pu generation. That is how a stable system operation is possible. So, load generation balance has always to be maintained. Okay. Now, suppose due to a power swing, the electrical center appears here on this line, okay, and the distance relays here see it as a zone 1 fault and open this line. Now, what will happen? The there will be two islands which are created, this island and this island. Okay. In neither of which there is load generation balance. Now, for synchronous operation, we have said that load generation balance always has to be maintained. In this case, what will happen? If you see here, here the load is greater than generation and here the generation is greater than load. Okay. So, here unless there is load shedding, stable operation will not be possible, and here the generator will have to be back down, which is something we want to avoid. Okay. So, here you will have to shed one of these loads, and then even then the system operate, because the swing has progressed too far, this is stable operation may not be possible. So, this you want to avoid. So, these two relays have to be blocked. Okay. So, what is known as power swing blocking feature. Okay. Now, as we said, the for a stable swings, it needs to be blocked as well as for unstable swings. Stable swings, because the system is going to recover. If you trip, there is no point. I mean, if there was a stable swing and in a stable swing the electrical center will never appear, but zone 3 can operate or zone 2 can operate, and then maybe again the same the swing was stable, but the power swing characteristic encroached on the zone 1. I am sorry, the zone 2 and zone 3 of R1 and R2, then though the system could have recovered, you have tripped the line, and this will make the situation worse. Okay. So, unstable swing, you may not have load generation unbalance. So, tripping on unstable swings is bad, tripping on stable swings is worse. Okay, because you have, where the system could have recovered, you have made it into probably an unrecoverable situation, and because the load generation balance could not be in the islands also has to be seen. Okay. So, now what do you have to do? Okay. You have to now identify islands like this. This could have been an island. Okay. I will just rub this out. Okay. This could have been one island. We will just okay. So, this could have been one island and the rest would have been another island. Okay. So, instead of, once you have blocked these two relays, you also have to now open issue a trip command via these two relays here. Okay. So, you have to do what is known as an out of step tripping to accompany the out of step blocking. And on power swing blocking is a feature that you have to provide. This is it. Okay, power swing blocking. I will just repeat it. Now, how do we achieve this? Okay, these both features is what we will look at next. Okay, traditionally this has been achieved using blinders. We will quickly have a look at the few slides and then we will come back to this discussion, so that it is a bit more. Okay, so this is again classifications. This is that example that we just saw, and how do we now block? Now, these are out of step blocking relays. Before that, let me explain the principle. Okay, just to explain the principle, we will first talk of blinders. Okay, this is not necessarily always executed using blinders, but to understand the principle, it's a very useful tool. Okay. Now, blinders are nothing but reactance relays. Okay. This is talking in terms of traditional electromechanical relays only. Okay. With numerical relays, you don't need different elements and all that, but here these are what are known as reactance relays. So, you have R and X. A reactance relay is simply a straight line on this Rx plane. So, you could place these lines. I will first draw the relay characteristic so that it is easier for us to understand. This is our distance relay Mo type. You have zone 1, then you have zone 2, and zone 3 as well. Now, if you see, the zone 3 area includes a very large part of the Rx plane. So, you could have for any small disturbance in which the Z or the impedance locus enters that characteristic, you could have a tripping. To avoid that, to exclude a large part, you use these blinders. Okay. So, as we said, the reactance relays or the reactance characteristic on the Rx plane is just a straight line. So, what you could do is place these lines like this. Okay. And have it operate only in this area. So, this side is operate and this side is block. Similarly, on the other side, okay, because it is symmetrical, your swing could or your locus could enter from either direction. So, you have a symmetrical blinder on the other side. Okay. So, now we excluded, if you notice, you have excluded this part of the area. So, only the useful what you have determined as useful, this part is this part of the zone 3 characteristic is still available. Okay. So, this is block and this is operate. You actually if you see how to in engineering wise, then you just have the contacts of the blinders in series with the trip coil. If this is your DC, I am not drawing all the elements, but suppose this is your DC positive and negative, and this is your breaker contact, this is your trip coil, and then you have the relay contact here, and if you have the two blinder contacts in series. Okay. So, only if the two blinder contacts close and the relay contact closes, if the characteristic enters it, then only in that case the relay will operate, okay, or issue a trip command and the trip or energize the trip coil and issue a trip command. Okay. So, these are blinders. This is not necessarily, or it is not a power swing blocking element. Now, to make it a power swing blocking element, what you need to do is you need two sets of blinders in parallel. Okay, or any characteristic in parallel, which we will see a bit later. We could have a Mo characteristic also, which is there on the slides, which we will go to a bit later. Since we are on this discussion, let us complete it. And what is usually done is, if this is a blinder, I am just continuing from the previous example, not drawing everything. If this is one blinder here, then you have another blinder here in parallel, and similarly on the other side you have a blinder and you have another blinder in parallel. Okay. So, what happens is, the basic principle is this. Okay. Once the either if there is a fault or a power swing, it is going to cross the locus, impedance locus is going to cross both these characteristics. It may so happen you have say zone 3 here. It may so happen that if it is a stable swing, that it could, of course, it could return from here also from zone 3, or it could return from, it could cross one blinder and return back, in which case there is no issue at all. but what if it crosses to both the blinders? Okay, there are two possibilities here. One is that it is a fault, and second that it is a swing. But the distinguishing feature is that a fault or faults cause instantaneous instantaneous change in impedance. So, at one time instant you are here, and at the other time instant it will instantaneously come into or change the position. Okay. So, swings on the other hand cause or result in a slow movement in the Rx plane. They are very slow frequency, that are in the range of 0.5 to 2 hertz. Okay. Why is this? Because there you have synchronous machines, you have machine inertias, and to change the rotor angles it takes time. So, the power swings will cause a slow movement. So, what you do is, once the locus crosses one blinder, you start the timer, and when it crosses the other timer, the other blinder, you stop the timer and you measure the time. If that time is less than a certain threshold, then it is a swing. Okay. If it is faster than that, then it is a fault, then you do not have to block the relay from operating. Okay. So, one way of doing it is these angles are known. Okay. Because if you have the line or the ZS, if you remember our discussion, you will have this as say delta delta 1, and the angle that the two ends of the line or the system subtend at at the second blinder is delta 2. Okay. So, now you know the swing frequency or you simulate the swings and you find the swing frequencies SF naught or SF. Okay. Now, to traverse 1 radian to traverse 360 degrees or 2 pi radians. In one it will traverse 2 pi radians. Okay. So, to traverse 1 radian, it will take SF naught. Okay. So, the time taken to traverse would be delta 2 minus delta 1 upon 2 pi SF naught. Okay. So, now this time, now this is critical, because how do you determine the time for the swings, okay, or how do you determine the swing frequency? So, for this there is no other option but to carry out multiple number of simulations and then actually find out the worst case or the fastest swing that can occur, okay, and then set the threshold slightly above that. Anything faster than that is the fault. So, this requires multiple simulations to be carried out. Multiple is very large number of simulations, because there is no other way to determine this, and that is why this is not a very foolproof kind of method. You may have missed some swing or you may have missed some particular fault which causes a very fast swing. So, this your time setting may not be correct and then the relay may not be blocked. Okay, your swing may be faster than the threshold that you have set, and then the relay thinks it is a fault and it may not block it. So, and multiple failures like this have known to have occurred. Okay. Now, one aspect that has to be taken care of is, of course, here one thing that needs to be mentioned is these blinders are actually reactance relays in when you are talking in terms of electromechanical relays. But these characteristics could be easily simulated in a numerical relay, and they could be present in the same numerical relay as well. Now, one thing that has to be remembered is what happens if there is a fault when the relay is blocked. Is blocked due to a power swing. Okay. In which case you have to unblock the relay. How do you detect that? Because this mechanism will still be on, the time of travel of the impedance locus, that it's still being tracked, and if that is faster than the time that is set for the power swing, then you know that it is a fault, and then you will have to unblock the relay. In the numerical relay, it is even more easier because it the impedance is being calculated at each time step, and you know the time step, so you can calculate the time of the fault. So, this has to be taken care of. There has to be unblocking if there is a fault. So, even if your relay is blocked due to a power swing, if there is a fault, then that gets precedence or priority, and it has to be unblocked. Okay. So, there are a few more schemes which we will see on the slides, and then the last scheme I will just discuss back here. So, this is what we discussed here. The transit time is larger than a preset interval, and then it is a swing and it will block. Okay. So, this is one of the ways of implementing this. You need two parallel characteristics, okay, so to determine how the impedance locus has traveled. Okay. So, this is one way of doing it. You have a larger more characteristic similar to the distance relay characteristic, and then you start the timer when it crosses that outer characteristic, and then stop it when it reaches your distance relay characteristic. So, instead of the straight lines that we saw in terms of reactance relays, this is similar to the relay itself. You have a Moe blocking relay. Okay. You could also have an offset Moe. Okay. This is a non-directional distance relay characteristic. You do not use the direction information, and similarly, when it crosses the first characteristic, you start the timer, and when it crosses the distance relay itself, you can stop the timer. So, you know the time of traversing of the impedance locus. Okay. So, here one thing that we have to keep in mind is that how do you implement the out of step tripping relay. Okay. Now, we will just show it with the same characteristic. Okay. This is your Rx plane, and here okay, you take the blinders on the other side also. Okay. So, what you do is, you could have sets of two. Okay, I will draw the two, but for this, in principle, only the inner blinders are necessary. So, if your impedance locus crosses this blinder, okay, and it crosses this one as well on the other side, your relay is here. Okay. Okay. That means definitely that it is an unstable swing, because your delta is not going to stop at 180 degrees. Okay, it will, once it crosses 180 degrees, this is your, I am again going back to the equal criterion figure. This is 180 degrees, this is your initial operating angle, this is 180 degrees. Once it crosses, it will continue to accelerate, okay, and then till it comes back to that. I mean, this situation will never occur in practice, but just for the theoretical discussion, it will continue. So, it will continue beyond 180 degrees and it will cross this one also. So, if it crosses this, then you know that it is an unstable swing, and then you have to block the operation of the two relays. You have already blocked because of this. Now, you have to, this is an OST, okay, out of step tripping. So, you have to now trip some other relay somewhere else where you have identified coherent set of generators, so that the islanding is successful, load generation balance is maintained, and the system can still continue to operate in a reduced form. Okay. So, this is how the blinders on the other side are utilized for out of step tripping. Now, just as a word of caution, you could have some swing which is actually very far away, okay, and since these characteristics continue, you have a swing very far away. So, the impedance is very low, okay. So, it does not matter, and to prevent operation here, then you have overcurrent relays also. You can think of them as like this, of characteristics like this, and then beyond this, any swing occurring beyond that is ignored. Again, this is very similar, very easy to implement in a numerical relay. In an electromechanical setup, you will need one more set of, other than the blinders, you will need an overcurrent relay as well. Okay. So, now there is just one more scheme. There are many other schemes, but we will discuss one scheme which is also popularly used for power swing blocking, which is known as the R dot scheme, or only the R dot scheme. Okay. So, here instead of the R x plane, we are using the R and dr by dt plane, or R dot plane in other words. The axes are R and R dot, and we will see how we implement the power swing blocking. Actually, the characteristic is something like this, okay, and this is block and this is operate. Okay, the set point is like this. R is the so this should be greater than I am sorry, less than or equal to 0. T1 is the slope of this line. R1 is the relay set point. This is this. Okay. Relay resistance set point. This of the R dot relay rather. Okay. So what happens is if there is a stable swing, you have seen that the impedance reduces. Okay. In the if you see it only in terms of R, it will also reduce, but if it is stable, then it will go back. Okay. But if it is an unstable swing, it will reduce very rapidly, and it may or may not go back like this. Okay. So, in this region, if it enters this region, then it is an unstable swing. Okay. This is stable, this is unstable, since it is and it meets our criteria of R minus R1 and T1 into dr by dt is less than 0. So, meets our criteria. This is because what happens is if there is an unstable swing, the reduction in R would be more rapid and can be detected faster than the with the blinder scheme. So, you have this has a better success rate than the blinder based power swing blocking relays, but it is still again the determining all this T1 and R1 and all that is still tricky. So, it is again not a very foolproof kind of system. So, none of these schemes that we discussed today are really foolproof. Okay. So, now that completes our discussion on distance relays, effect of power swings on distance relays and distance relay blocking schemes. from the next lecture we will move to the second part of the course, which is the fundamentals of numerical relaying. Okay, what are numerical relays, how phasor estimation is done, and some aspects of signal processing, etc. Okay, so we will stop here today. Thank you.